A stone blade is pressed into a wooden handle. One strike, and it twists. The edge slips toward the hand. The stone may break, the handle may split, and the sharpest part of the tool can turn against the person holding it. People faced this problem long before pottery existed. By at least 191,000 years ago, people were using birch-bark tar on stone tools over 100,000 years before the earliest known pottery. So the first answer is simple. Pottery was not required. Experiments show that fire, stone, ash, and earth can be enough to produce and collect birch tar. But that answer hides the harder part. Something sticky still had to keep a blade stable through cutting, scraping, twisting, and impact. And glue was not the beginning of composite tools. At Kathu Panwan in South Africa, stone points 500,000 years old show evidence consistent with hafting. Some were probably attached to shafts long before any adhesive from the site survived. A split socket may have gripped the stone. Fiber, hide, or sinew may have bound it. A wedge or shrinking wood may have tightened the joint. We do not know the exact method. Glue, therefore, entered an older technology. The real question is not only how people made adhesive before pottery, but what extra failure it prevented when sockets and bindings already existed. The clearest early evidence begins with 2 stone flakes from Campitello Quarry in Italy. Dark material covered parts of the flakes away from their main working edges. Chemical analysis identified the substance as birch-bark tar, and its position strongly supports a hafting or backing function. The deposit is at least 191,000 years old, and may be older. But the evidence has strict limits. No wooden handle survived. No production structure was found. The tar does not reveal the exact method used to make it, and the site alone cannot identify the maker with certainty. Those limits matter, because a black residue on ancient stone is not automatically glue. It might come from soil, smoke, contamination, storage chemicals, or the material the tool once worked. Researchers must identify the substance, examine where it sits on the tool, compare it with the working edge, and rule out other sources. Campitello answers 2 questions well. It tells us what the material was, and it strongly suggests what it was doing on the stone. It does not tell us how people produced it. That missing step creates the central puzzle, because birch bark is not a lump of ready-made adhesive. Some trees release resin that can be collected directly. Birch bark is different. To obtain tar, the bark must be heated. Heat releases volatile compounds, and those compounds must cool and condense into a dark, sticky material. In practice, that creates several ways to fail. If the bark is not heated enough, very little tar forms. If too much oxygen reaches it, the bark and the useful compounds may simply burn. Even if tar forms, it must condense somewhere accessible instead of disappearing into the fire or soaking into the ground. For a long time, this seemed to require a sealed, low-oxygen installation with one area for heating and another for collecting the product. If that had been the only workable method, birch tar would have demanded a carefully planned multi-step process. Experiments showed that it was not the only method. In one simple approach, birch bark is burned near an inclined stone surface. Small amounts of tar condense on the cooler stone and can be scraped away. Other experiments place rolled bark beneath ash, embers, soil, or inside a shallow pit. These materials restrict direct burning and allow tar to collect nearby or below. More elaborate underground arrangements can also work. None of these methods requires pottery. Stone, fire, ash, earth, and a prepared surface can be enough. The yield may be small. Some attempts fail. A large amount of bark may produce only a limited amount of adhesive. But the experiments prove that ceramic containers were never a necessary condition. They do not prove which method was used at Campitello. An experiment demonstrates possibility, not history. A technique that works today may never have been used at a particular prehistoric site. But experiments can eliminate false requirements. If tar can be produced without pottery, then the absence of pottery cannot explain away the archaeological evidence. The same experiments also weaken another common claim. The mere presence of birch tar does not automatically prove that its makers used a highly controlled underground distillation system. A usable product can form through much simpler processes. But that does not mean every prehistoric tar sample came from the simplest process. At Königsau in Germany, 2 pieces of birch tar survived from a broad period between roughly 80,000 and 45,000 years ago. Researchers compared their chemical composition and internal structure with tar produced through several experimental methods. The archaeological samples were judged to fit better with production under restricted oxygen, possibly in an underground arrangement. That conclusion is not a photograph of an ancient tar kiln. No complete production structure survived beside the material. The inference comes from comparing the tar with experimental products, and burial, aging, and contamination can complicate that comparison. Still, Koenigsau changes the answer again. Simple methods could produce tar, but prehistoric people were not necessarily limited to them. Different levels of technical control may have existed within the same broad period. There was no guaranteed straight line from one primitive method to one advanced method. Simple and more controlled procedures may have coexisted because they required different amounts of time, fuel, preparation, or reliability. And outside birch-rich parts of Europe, people often solved the same joining problem with completely different materials. At el-Tlel in Syria, stone tools carried natural bitumen. Unlike birch tar, bitumen did not have to be created from bark. It could be obtained from natural deposits, then cleaned, softened, heated, or otherwise prepared. At Fossalone and Sant'Agostino in Italy, residues on several tools were identified as conifer resin. One Fossalone sample also contained beeswax. These materials appeared not only on large hunting points, but on scrapers, Levallois flakes, and other relatively small stone tools. At Cebudu in South Africa, residues associated with hafting include ochre and organic materials. Experiments show that plant-based adhesives mixed with mineral particles can form effective joints. But the exact archaeological recipes have not been fully recovered, and not every red mineral residue should be treated as a functional glue ingredient. Together, these sites reveal three broad routes. Some adhesives, such as natural bitumen or certain resins, could be collected directly and then softened, cleaned, dried, or concentrated. Birch tar had to be created through heat transformation. Other mixtures could be adjusted with wax, ochre, or mineral fillers. The local landscape therefore shaped the technology. A group living near natural bitumen faced a different problem from one surrounded by birch trees. One had to find and prepare a material already present in the environment. The other had to transform bark into a new substance. But obtaining something sticky was not enough. A material can adhere to stone and still fail as part of a tool. Some resins soften when warm. Other mixtures become brittle in cold conditions. A glue may resist slow pulling but fail when the stone twists. A material that works on a smooth test surface may behave very differently between rough stone and fibrous wood. Before hardening, the adhesive must be workable. If it is too stiff, it cannot fill the irregular gap between stone and handle. If it is too fluid, the stone may move before the joint stabilizes. After hardening, it must resist several kinds of force. Cutting creates sideways shear. Scraping can twist the stone. A projectile point experiences sudden impact. Moisture and temperature can change the material during use. This is why the strongest adhesive in a simple test is not automatically the best adhesive for a prehistoric tool. Experiments with plant gums, ochre, quartz particles, resins, and tar show that performance depends on the entire combination: the base adhesive, the size and amount of added particles, the roughness of the contact surfaces, the thickness of the adhesive layer, and the shape of the joint. Ochre is a good example. It is tempting to say that prehistoric people added ochre because it always made glue stronger. The evidence does not support that universal claim. Under some conditions, mineral particles can change viscosity, toughness, or resistance to moisture. Under others, they may weaken the bond. Particle size and the underlying adhesive may matter as much as the mineral itself. Beeswax may also change how resin behaves, including its softness or working temperature. But finding wax and resin together does not reveal a complete recipe, and it does not prove that every mixture was designed for the same purpose. To know whether an adhesive actually worked, the material cannot be studied alone. The entire joint matters. The stone supplies hardness, sharpness, and wear resistance. The wooden handle supplies grip, leverage, distance, and a structure that can absorb movement. Adhesive reduces sliding and rotation. Fiber wrapping can resist tension and help stop the socket from opening. The shape of the slot and the roughness of the surfaces determine where stress becomes concentrated. Remove one part and the failure changes. Without enough adhesive, the stone may rotate inside the socket. Without wrapping, the handle may open under load. With a poor slot shape, force may concentrate at one point and split the wood. With an adhesive that is too brittle, cracks may spread through the bond. The same glue can perform well in one haft and badly in another. That is the bridge between making glue and making a tool. A substance was not useful simply because people could produce it. It was useful only when its properties matched a particular joint and a particular task. The evidence from Fossalone and Sant'Agostino expands that task beyond the familiar image of a spear point. Resin was found on different kinds of smaller stone tools. Their exact uses cannot always be recovered, but the evidence suggests adhesive technology was not reserved only for rare hunting weapons. It may have been part of cutting, scraping, hide processing, woodworking, and other ordinary activities. This also exposes a major distortion in the archaeological record. Stone survives extremely well. Wooden handles decay. Fibers disappear. Adhesive oxidizes, breaks down, or remains only as microscopic patches. A complete tool can enter the ground as stone, wood, binding, and glue, then emerge tens of thousands of years later as a single stone flake. The object displayed as a stone tool may therefore be only the most durable survivor of a much more complicated object. Some adhesives can also be softened again with heat. In experiments, that can make repositioning or rehafting a stone component possible. It may have allowed a damaged stone part to be replaced while preserving a harder-to-produce handle. But that remains a technical possibility, not direct proof that the earliest tar-back tools were routinely repaired or designed as modern modular systems. We can now answer the original question directly. Prehistoric people did not need pottery because they were not following one universal recipe. Some adhesives could be collected from natural deposits. Some resins could be softened, concentrated, or combined with other substances. Birch bark could be transformed with fire while stone, ash, soil, and pits controlled where heat and oxygen reached it and where tar condensed. More restricted underground methods were also possible, and at least some archaeological tar has been interpreted as the product of such a process. But producing a sticky substance was only half the achievement. Stone is sharp and wear-resistant, but it is brittle and difficult to hold safely. Wood is tough, light, and easy to grip, but it cannot maintain a stone-like cutting edge. Fiber is strong in tension, but it cannot cut or pierce. Adhesive can connect these materials, but it cannot become a useful tool by itself. The joint allowed each imperfect material to perform the task it did best. The stone could cut. The wood could provide leverage. The fibers could resist tension. The adhesive could prevent movement and keep the parts working together. Instead of searching for one perfect material that was simultaneously sharp, tough, light, comfortable to hold, and resistant to pulling, prehistoric toolmakers could combine several imperfect materials into something none of them could become alone. That is the deeper importance of prehistoric glue. Archaeologists call these periods the Stone Age, largely because stone dominates what survives. But many of the most capable tools were never just stone. They were stone, wood, fiber, and adhesive, joined through knowledge that has mostly disappeared with the organic parts. Prehistoric people did not invent one glue on one day. Different groups used different raw materials, and some methods were simpler than others. They collected natural adhesives, transformed bark with heat, adjusted other substances through warming, drying, and mixing, and learned through experience what would hold inside a working joint. They made glue long before pottery because pottery was never the essential requirement. Fire, stone, ash, earth, locally available materials, and controlled handling were enough. And the decisive breakthrough was not merely discovering something sticky, it was learning how to make different materials work together.